it's very that it is very late in the day and they have to stop the game and they plan to again start the game in the next morning. So in this scenario, there is a problem because if Alice plays her turn before stopping the game, then Bob will have the entire night to think of his next move. So that would give him an unfair advantage. And on the other hand, if Alice doesn't play, she will have the entire night to think about her move. So the question is that, is there a way to get rid of this solution? And one of the, is there a way to get rid of this problem? And one of the solution is that if there is a trusted referee wherein Alice can write down her next step and put it into an envelope and give it to the referee who may announce it in the next morning about her next move. So because we are assuming that the referee is a trusted referee, so Alice will not be able to change her next move once she gives it to the referee. And also Bob will be not able to know what Alice has written in the envelope till the next morning. So actually, these kind of games are played in the Japanese and Chinese chess, and it is actually called a sealed move. So the main question is that, is it possible to accomplish the above task without the presence of a trusted referee? And actually, this kind of problem was introduced by Blum, wherein he assumed certain computational restrictions on the parties. So we will talk about this problem in the information theory scenario. And this problem was actually introduced by Winter, Nascimento, and Imai in the information theory, from the information theory point of view. So the problem, as you can see in the diagram here, is that Alice wants to send some messages to Bob such that the messages are secure from Bob until Alice reveals the message to Bob, and she wants to transmit these messages over a noisy channel. So, and we also want to ensure that until Alice tells the message to Bob, Bob should not be able to know what Alice has actually planned to send it to him over the noisy channel. And Winter, Nascimento, and Imai showed that for the case of a classical channel, they showed that if we want these two conditions to be satisfied, that is, Alice should not change her mind while revealing her messages to Bob, and vice versa, that Bob should not be able to know anything about the message until Alice reveals it to him. So under these two constraints, Winter, Nascimento, and Imai showed that the commitment capacity of a classical channel is given by the conditional entropy of X given Y, where X is the channel input and Y the channel output, and we maximize it over the input distribution. So in their paper, they had also claimed that whatever they have done would also hold for the classical quantum channels. However, they didn't give a proof. They just stated it as a theorem, and we couldn't find a proof of that statement. So me and Professor Hayashi tried to find a proof for this problem, and then we eventually realized that it is not so straightforward to claim such a result for the classical quantum channel, that there are certain issues which I will highlight in this talk. But before that, let me tell you the whole scenario here once again. So for the commitment schemes, there are two steps. So the first step is the commit phase, and the next phase is the reveal phase. So in the commit phase, so suppose Alice wants to send some message M, which is chosen uniformly. So what she does is that depending upon what message she wants to send and her private randomness, she applies some function to her message M and her private randomness, and then she communicates it over the channel to Bob. So what the channel does is that it spits out a quantum state depending upon the input which Alice had sent to the channel. Also, Alice sends a classical input to Bob over NO as this channel. So what she does is that depending upon the message she wants to send, and depending upon her private randomness, she applies some function, and in the end, she sends some U1 to Bob. So this is the first step of the commit phase. In the next phase, what Bob does is that, you know, uh, depending upon the input U1, which Bob has received in the first step from Alice, and the state which Bob has received, Bob tries to, Bob measures the channel output, which is WX1 here. So he does this operation coherently using some quantum instrument, and when he measures it, there is some classical output which is represented in terms of V1, and the quantum state after the measurement is quantified in terms of Y1 prime. So after obtaining this output V1, so Bob sends it back to Alice, and then in general in the ith round, depending upon the input received from the Bob, Alice applied some function on her chosen message, her input private randomness, and the input variable from Bob in the I-1th step, and she again does the same thing, applies some function and sends it across to the channel to Bob. So this sort of finishes the ith round of communication between Alice and Bob. But there is one property which we want in our commit phase, is that, so another thing is that, like in our talk, we will assume that, when Alice is honest, we will denote her operations by, by some collection of operations, which we represent it as A1M. So where A1M represents, Alice's operation for the message M. And similarly, because the Bob apply some POVM, so that is represented in terms of this B here, and if it behaves in a very arbitrary fashion, then we denote it by B prime. So one of the property which we want in our commit phase is that for any pair of the messages in the message set, the joint state induced, like for any pair of the messages, they should be epsilon close. So basically what it means is that this condition would ensure that Bob is not able to get anything about what was the message Alice, which was Alice trying to send it to him. And here we assume two kind of cases. One is passive Bob and the other is the active Bob. So by passive Bob, we mean to say that, Bob is being honest, and by active Bob, we mean to say that Bob is behaving in an arbitrary way and is trying to cheat to Alice. And in the next phase, which is the reveal phase. So in the reveal phase, what Alice does is that she reveals the message to M, and she also reveals her private randomness to Bob. And depending upon this M and Z, which Alice has revealed, Bob applies some decoding POVM on the state which he has. And what we want is that with very high probability, the message M is accepted if both Alice and Bob are behaving honestly. But however, if any of the parties are behaving in an arbitrary way, then we want that, that the wrong message should be accepted with very small probabilities. So here, when we say passive Alice, we mean to say that Alice is only cheating in the reveal phase. That is, she is revealing some arbitrary M from this set. But when we say active Alice, we mean to say that she may also cheat in the commit phase. That is, she is sending some arbitrary input sequences in this CQ channel. So actually, this tuple, which is A1, A2, B, and tau, is called the protocol P with n rounds, where this A1 and A2 represents Alice's operation in the reveal and in the commit and reveal phase, and here B and O reveals Bob's operation in the uh, commit and reveal phase. And here we define certain parameters. So where here is epsilon is the concealing parameter, that is for any two pair of messages, the state induced should be, like the distance between the state induced should be epsilon close in the L1 distance, and this binding parameter is that, if Alice and Bob behaves in an arbitrary way, then the wrong message should be accepted with probability at most delta. And here these things A and small p represent the thing that, the parties are behaving either actively or passively. So basically our aim is to, find a sequence of protocols such that we maximize the rate of communication as the number of channel users increases, under the constraint that, both these concealing and a binding parameter, they both go to 0 as the number of channel users increases. And the supremum of all achievable rate is called as the commitment capacity of the channel, and we actually define various notions of it in our work. So in particular, we define, CA and CP, where A means, this active and passive attacks. So actually, like in our work, we observed that it is not easy to discuss a general protocol, and one of the reason is that in the commit phase, once Bob measures the quantum state, that state is just this state just changes to some other state, and because we don't have an handle to it, and also Bob can behave in a very arbitrary way, so in general it is very difficult to ensure both the concealing parameter and the binding parameter go to 0. So to overcome this, we make an assumption that, we have we have a condition which we call as the invertibility condition. And basically what it means is that, at every step in the commit phase, there exists a CPTP map such that we can recover the original state from the measured state. So for this special case, we define, which is something called the commitment capacity of the case, when the parties are have the assumption that, where we assume that, we have this invertibility condition, and this A and P is again for the active and passive attacks from Alice and Bob. And further, we assume here that this non-redundancy condition, basically what it says is that for every X, the channel output cannot be represented as a convex combination of the channel outputs with respect to other inputs. So this condition is an important condition, but we can actually remove this assumption if we assume that the size of the set over which this X takes values is finite. So under this non-redundancy condition, we show that, for the case of non-interactive protocols, and for the case when we have this invertibility assumption, we show that the capacity in these special cases is actually equal to the conditional entropy of X given Y, and we again like supremize over the input distribution, which is same as what Winter et al. Proved for the normal classical channels. So actually we arrive at our result in 2 steps. So we first show that for the invertible protocols, the capacity has this upper bound in terms of the conditional entropy. So that is the converse. And then we show a protocol where parties are not interacting. So this non means that, there is just one node of communication. There is no interaction between the parties. So in this case, we design a protocol, and we show that we can achieve this rate of which is given by in terms of the conditional entropy of X given Y. So as I told you already that, like what we mean to say by the class of invertible protocols, basically it means that, like at every step after the measurement, we are able to get back the original state. So basically it means that, that the state induced at the end of the commit phase. So one thing to observe here is that the state induced at the end of the commit phase constitutes of the random variables m, xn, un, vn, and z, where m is the message being sent, xn is the input to the channel, un is the, depending upon the message m and the private randomness what Alice is sending to Bob over NY channel. Vn is the random variable which Bob gets after the measurement of the quantum state, and Z is the Alice's private randomness. So basically, at the end of the commit phase, the joint states consist of mxn, un, vn, z, and the quantum system y prime n. So where y prime n is the measured state in the nth step. So basically, when we say that the protocol is invertible, so it means to say that if we apply the above sequence of the invertible maps, then the state induced at Bob's end after their application, like we will get back the original state yn. I mean, essentially that's what it means for the protocol to be invertible. And in this case, like if we call the first state as rho 2 and the second state as rho 3, it can be seen that, both the states rho 2 and rho 3 are information theoretically equivalent. So what I mean to say is that the conditional entropy of xn given yn and un with respect to the state rho 3 is same as the conditional entropy of the sequence xn given un, vn, and y prime n with respect to the state rho 2. So with this observation, and together with one of the main result of our paper, wherein we show that, there exists a function h which will be able to estimate m with very high probability using this xn, un, and vn. So with this so basically, like with this observation that rho 2 and rho 3 are information theoretically equivalent, and with this derivation of this estimation function, we basically are able to show a converse, and basically the converse depends upon the continuity of the von Neumann entropy and the Fano's inequality. And the thing is that showing the existence of H is not so straightforward, and it requires some some non-trivial construction of some special functions. So to discuss more on this H, so one thing to observe here is that we are able to estimate the message M irrespective of the channel output. And we need this property of H because in the quantum setting, the state Yn is completely lost in the interactive protocol of the commit phase. So actually, Winter et al. Also used a similar strategy to prove a converse, but their estimation function depends on yn, and they could do it because in the classical case, I mean, even after the n lot of communication, I mean, you don't get like you still have yn, like because classically the state doesn't change whether it, like before and after the measurement. So to take care of this, we had to invent this H, which estimates the message M from xn, un, and vn independent of the output quantum state from the CQ channel. And to prove our achievability result, so basically we show the existence of a code. So basically this 2 raised to n R1 represents the number of messages, and for every message we have a code of size 2 raised to n R2. So here if you see that we have an upper bound of R1 plus R2, and that is basically because, I mean, to make sure that Alice is not cheating, that is, she is not revealing some arbitrary message to Bob. And if she does that, then that message is not accepted with high probability. Uh, with, we concentrate on the Hamming distance between any two pair of ports. So this upper bound on the sum rate ensures that if this ensures that that the Hamming distance between any two pair of ports would be bigger than some certain threshold, and because of which Alice will not be able to cheat. And the second criteria you would expect from any wire type channel kind of result, that basically it is for a concealing property, and it comes from many standard results using a decoupling. So basically our protocol is based on the quantum extension of a recently like a very recent paper by Masaito Hayashi in the classical case for list decoding. And basically we this achievability protocol is the quantum version of his protocol in the classical setting of a list decoding. So I would just now summarize this. So basically we prove that in the case of non-interactive protocols and in the case of invertible protocols, whether the parties are active or passive, we show that the commitment capacity is the conditional entropy of x given y, where and then we maximize this conditional entropy over the input distribution. So you can see more details about this work on this archive link. And yeah, and with this I would just like to thank you very much.
Thanks for the interesting talk. Any comments and questions? If no, so let's thank Naqueeb again. Thank you. And let's thank all the speakers. Thank you very much. So, Masahito, would you like to announce something? No?
Nothing. But maybe I will. Okay. I will open the breakout room. So if you want to discuss more privately, so please you can discuss. Once it disappears, so I will close this session. And the next session will be start 7 o'clock in China. So we have after our evening session, we have a music session. And also, I'm very sorry, I had so many very serious trouble for my laptop. So at that time, my laptop does not work well. And also, very strangely, once I log in Zoom, but I could not start